In this video, we'll discuss another situation in which you need multiple integrals to set up an area of a certain region in the plane. So sometimes these areas are not that easy to figure out using an integral, mainly because the ones we saw before, there's always one function on top, one function on the bottom, and it's easy to find the area that way. Sometimes that's not always the case, and to do this, you need a little more trickery in how you set up the problem to be able to solve it correctly. And you should think back to what we did in the last couple of videos where we had curves crossing to make sure we had to say which function is on top, which function on the bottom. That's going to come into play again here. So a region like this is something like this. So let's say I want to find the area of this orange region here. Well, it's pretty simple. There's graphs of functions on all sides. That's great and easy to work with. But the issue is there's not always a single function on top or on bottom, right? For one part, the green function is on top and then the x-axis on the bottom, or the blue line is on the bottom. For the other part, the purple curve is on the top and the blue line's on the bottom, or the x-axis on the bottom. So how do we handle these sorts of problems? Well, we need to, again, split it up into different regions. If we can split this up into a way where we know that in one chunk, one function is on top, and in the other function is on top, then I can just do those two parts separately and work forward from there. So the idea here is splitting my region that is not vertically simple, i.e. there is not one function always on top, one function always on bottom, into separate regions, both of which are vertically simple. So if I draw in one more line down the middle here, we now see this region here is vertically simple, as is this one. So I know how to find the area of each of those two smaller regions, then I can just add them together to find the area of the whole region. So this is similar to having to split at intersection points before, but now we're just splitting because of the function that's on top, not because our two bounding functions crossed in the middle of this domain. So again, the only real trick, figure out which function is on top when, and use that to determine your integral. And that's the main part of the process there. Set that up first, figure out how you're going to decompose your region into multiple parts that are vertically simple, and then go through the process for each of those regions like normal, and add them up at the end. And that's sort of what we've got in this page here. For pretty much every case that you come across, it's possible to split the region into different chunks, each of which are vertically simple, and then you can put multiple integrals together to find the total area of that region. So basically, figure out the curves that bound your region and figure out where they cross. You then want to use these intersection points to break your region into different chunks, all of which are vertically simple. And then you want to go through and find the area of each of these chunks, and then add them up to get your total answer. That's really the idea behind all these problems. So let's see an example of how this works, and you can see how it all comes together to give you an area of a region that you wouldn't be able to find by just one integral before. So find the area bounded by the graphs of y equals 2x, y equals 5x, and y equals minus x plus 12. So this is going to be 3 lines, 2 with a positive slope that go through the origin, and then 1 with a negative slope that has a higher intercept. So the graph is something like this. And I want to find the area of this region in here. Now note that this is not vertically simple. There's no one function on top the entire way. The green line's always on the bottom, but the top line switches from orange to purple halfway through. So to build this up, we need to find all these intersection points. Well, this one here I know is the origin. Let's find the other two. So for the other two, we need to figure out where these lines intersect. So for the green and the purple, I want 2x equals minus x plus 12, 3x equals 12, or x equals 4. So green and purple cross at x equals 4, and therefore y equals 8. And then for orange and purple, I want to plug those two together. So I want 5x equals minus x plus 12, 6x equals 12, or x equals 2. So this will cross here at 2 and 10. Now, what that means is if I draw a vertical line down here at 2, I will now have split my region into 2 chunks, each of which are vertically simple. One has orange on top, green on bottom. One has purple on top, green on bottom. So I can find those two areas on their own and then add them up. So my total area is going to be an integral from 0 to 2 of orange minus green plus an integral from 2 to 4 of purple minus green. And now we just have to solve out these integrals. This will be an integral from 0 to 2 of 3x dx plus an integral from 2 to 4 of 12 minus 3x dx. Then we can find antiderivatives. 3x squared over 2 from 0 to 2 plus 12x minus 3x squared over 2 from 2 to 4. Then we can plug in our answers. 0 here gives me 0, which all comes out to 12. So that's the idea for these multiple vertically simple regions problems where there is usually a point we have to split the region in half, where one half you have function on top and the bottom, the second half you have function on top and bottom as well, but one of those functions is not the same. And you can work out the areas just like normal and add them together to get your final answer here for these sorts of problems.